Hello, everyone. Welcome to our, what is this, Wednesday, March 1st live session. My name is Matthew. I am one of the online instructors, course managers for online classes. We are here with Vicky, who's helping out with all of our video stuff behind the scene. Chris, I'm going to hand this over to you, and then I will, actually, let me explain how we run this in case you're new. Please post your questions in the chat. We will select them from there. We generally try to go in order, but we jump around to try and get a variety of question askers and topics. And
email is okay too.
Yes, that's right. And you can send an email in as well to our email address, and that will be posted in the chat. And I will hand this over to you, Chris, to welcome everyone, and then we'll get started with questions.
Okay. Good. Hello, everyone. We have to finish promptly or a few minutes early, so we'll get started right away. Good to have you all here for the live session, open to anyone in our courses or just who finds this stream that we do every few weeks. And I'll just start right away. Questions on astronomy. Floor is open.
All right. The first question is from Egil Scala, who's on with us live. Astronomers say the Milky Way consists of about 100 billion to 400 billion stars. Why is there a 4 times discrepancy?
It's a good question. And it basically amounts to the fact that it's very hard to count the stars when you have to go to the very dim limit of stars. So by far the greatest number of those stars, the vast majority of them, and I think the true number is closer to 400 billion than 100 billion, are red dwarf stars. They're much less massive than the sun. So red dwarfs go down to the fusion limit, which is 8% of the mass of the sun, and their luminosities or brightnesses are hundreds to thousands of times less than the sun. So they're extremely dim. And so you actually can't see or count representatively all the red dwarfs in the Milky Way galaxy because they're very faint, and the ones at the far edge of the disk are very far away, or in the halo are far away. So it is at some level an estimate, and it's an extrapolation down to the fusion limit. And that's why there's intrinsic uncertainty. But given the predominantly red dwarf nature of the stellar populations, where essentially there are 1,000 red dwarfs for every star that's exactly like the sun, that 400 billion is about the right number, and it's overwhelmingly red dwarf stars.
Excellent. That's a really interesting challenge. The next question from one of our live participants, David Learning, asks, in the last 50 years, what is the most significant theory of astronomy that has been overturned?
That's an interesting question. If the time frame was a little longer than 50 years, then I would say the steady state theory, that the idea that the universe had not essentially evolved over time, but was still expanding. And I suppose that almost doesn't get in the time frame because the Big Bang was essentially confirmed with the microwave background in 1964. So that's more than 50 years ago. Within 50 years, there are no enormously influential theories that I would say have been overturned in astronomy or in astrophysics. The field has generally moved and progressed quite smoothly. So foundational things like that, like overturning a theory, probably only happen a couple of times in a century.
The next question is from Yangip, who's on with us live. Can you talk about how parabolas are used in astronomy and possibly in coordinate space or coordinate dimensions? Can you talk a little bit about the mathematics of?
Certainly, a parabola, is a mathematical form that describes the motion of a moving object in a gravitational field, for example. So it's just common. It's a common shape in mechanics. But if you're talking about more fundamentally and mathematically, you have the idea of conic sections. So if you imagine a cylinder, a 3-dimensional cylinder, and you take a cross section through the cylinder, if you take a horizontal cross section, that's a circle. If you take a tilted cross section to the horizontal plane, that becomes an ellipse. And so you can describe the general category of ellipses by intersections with that conic section. And you can also take different intersections which lead to a parabolic shape, and then you generate a family of parabolas. So a parabola is just part of a family of conic sections, but it also physically corresponds to the motion of objects under the force of gravity, for example.
Thank you. The next question is from Lawrence 4040. This is regarding black holes, and they'd like to know, isn't the mass of a black hole increasing faster than the rate at which the black hole is evaporating or might evaporate, if that is true?
Yes, it is definitely the case that the evaporation rate by Hawking radiation of black holes is incredibly slow. For a star like the sun, a massive black hole that has the mass of the sun won't die that way, but there are black holes that are mass of the sun or a few times that. The evaporation time is 10 to the 68 years. It's one with 68 zeros after it, so incredibly slow. And for a black hole that's in a binary system, mass is being spooned on to the star, the black hole, at a rate of maybe 1% of the mass of the companion, so 1% of the solar mass per year even. Black holes in the center of galaxies are also evaporating with a very long time scale, and they are also fueling and growing by the rate of maybe 1 solar mass per year. So yes, growth of black holes by mass transfer in binary systems, if they're small black holes, or just consuming gas and stars whole, if they're the center of galaxies, is orders of magnitude faster than the evaporation rate.
The next question is from an email from Peter. National Geographic magazine recently published a fascinating article. Oops, sorry. How the ancient paper folding art of origami is being used in various branches of science and technology, including astronomy. How realistic is it for origami star shade technology to be used to detect exoplanets?
It's an interesting idea. Some would argue that the James Webb Space Telescope was a sort of fairly simple form of origami when it unfolded all its mirrors to take its final configuration. So that might be an example of origami used for a very important space project. Star shades do have quite complex shapes. They have petals, essentially. They look almost like flowers. So they have many different surfaces and many components, and unfolding them in orbit is best done in a sort of origami sense. You have to plan how this petals unfold and then lock into place. So I would say it's definitely the case that techniques of origami would be applied when we get the star shades deployed, because remember, they have to fold and pack into a much smaller space than the enormous extent of the star shade itself once it's in orbit.
The next question is about the astronomical object, the pillars of creation. Hamid would like to know, what is the origin of something like the pillars of creation? How much mass is there? Did all of that stuff originate from supernova? Like, where did all of that, those clouds come from?
Right. The pillars of creation, which is of course the colloquial name for this star forming region, is a very active area of star formation in the plane of the Milky Way galaxy, not too distant, a few hundred light years from Earth, I think. This is typical of other regions like the Orion star forming region or the Taurus star forming region. So we know of a number of these. And these are typically regions where dozens, if not hundreds, of stars are forming. So what we see in the pillars of creation is at the top of the towers of gas, of nebulosity, we see stars actually forming. And those stars in their radiation is actually heating and ablating the tops of the pillars. So that explains the interesting geometry of the pillars of creation. And that's a pretty routine configuration. That particular geometry is rather unusual and very beautiful, of course. But that's not unusual for how stars form. They form in complex, chaotic regions of gas where the gas is forming the stars, but also is being irradiated by the stars and blown away by the stars. So it's a rather complex interplay of gas moving into stars and forming them, and then gas being ejected by the young stars and clearing out that neighborhood.
Just Doll 88, who's on with us live, would like to know, are we any closer to evidence of the unification theory and reconciling general relativity with quantum mechanics since, I guess, since the class video was made, she asks, but what has been the latest major discovery in this area?
Progress in this area has been slow because it's a very difficult problem. Einstein worked on it for over 20 years without success. So we know it's a hard problem. Very clever astrophysicists and physicists are working on it, where string theory is the best candidate for a theory that would unify quantum theory and general relativity, the two theories of nature that work each on their own extremely well, but are incompatible with each other. We need an overarching theory that is the theory of everything, essentially. The trouble is that the scales at which this theory of everything would operate and could be tested are incredibly small compared to the smallest scales we can access with a microscope, say, or any technique. And the energy scales are fantastically high, much higher than we can access with any accelerator. So it's a very difficult theory just to work the theory, and it's also extremely difficult to test. And for both of those reasons, I think progress has been pretty slow, but people haven't given up on string theory, for example. There's still a very active community working on it.
The next question is from a pasta pastor who would like to know, in current news, astronauts in the International Space Station are going to be staying longer than expected. There are worries about radiation damage, et cetera, to them. Is there a current max time in space that we won't cross, like absolutely? And how might that affect Mars and Moon missions?
Well, there are astronauts, there are a few astronauts now who've spent long durations in Earth orbit. A number of American astronauts have spent a year to a year and a half. I think the Soviet cosmonaut with the records around 800 and something days, so that's over 2 years. And there is serious health damage at that point. All astronauts who spent over a year in orbit have had health issues, but they're not usually reversible and they're not fatal, for example. Mars missions are going to take a long time. The return trip is 8 months each way, plus however long you spend on the surface. So it's probably 2 years as well. And also you're beyond the protection of the Earth's magnetic field. So in interplanetary space, the radiation dose is even higher than it is in Earth orbit. And so these are health issues that so far there's no guideline as to what's the maximum allowable. It's just a risk. The dose you would get on a trip to Mars is equivalent to a lifetime of radiation exposure on the Earth. You get it in 8 months, but on the other hand, it increases incrementally your chances of certain cancers just by a few percent. So it's not a dramatic risk. In fact, it's far less than the risks of the mission failing or of being stranded in space or stranded on Mars. So I think radiation is an issue, but it's not proving to be a showstopper for any of these long duration missions.
Excellent. The next question is from an email that Wendy sent. She's always got great physics questions. This one is, dark matter has been theorized as a superfluid with unusual properties. What do you think of this idea or hypothesis?
People are stretching and reaching for various ideas in the absence of knowing what dark matter is. The idea that dark matter is a superfluid is interesting, but it doesn't have much of a physical basis yet in terms of a prediction that we can test. It actually is still more logical and easier to visualize dark matter as a small subatomic particle with no electromagnetic interactions. Something like a neutrino, but more massive than a neutrino. You can hypothesize dark matter as a superfluid, but that still begs the question of what its fundamental physical nature is and what its microscopic fundamental particle equivalent is. So I've seen, articles about the superfluid nature of dark matter, and it does indeed behave in some ways like that, but that still doesn't answer the question of what the fundamental entity that corresponds to dark matter is.
The next question is from David George Pulley. In the first lecture in one of our courses, it was said that hot Jupiters were in very eccentric orbits, but in close to star orbits, won't the orbit circularize quickly?
Yes, I mean, that was probably too blanket a statement. Some hot Jupiters are in elliptical orbits, and some have been tidally locked and circularized by their star. It also depends on their evolutionary state, because it does if an orbit is initially quite highly elliptical, it does take a significant amount of time to circularize the orbit and for this planet to become tidally locked. So if the planets have originally been in more chaotic orbits, and as we think have migrated from further out where they could have had highly elliptical orbits, you will expect to see some that are have a certain eccentricity. But eventually, and in the end, they will all circularize, and many will fall into their star. And so we don't see all the hot Jupiters anyway, because some of them have essentially been consumed by the star.
B. Mitchell, 825, is on with us live and asks a question I believe we've had before, but it's always good to address these because I know people have a lot of interest in it. Could black holes be the source of dark matter or dark energy?
There have been some recent research ideas that are trying to connect black holes and dark matter. And most physicists think that's a bit of a stretch. The best thing we can say is that black holes will include dark matter along with normal matter because they form from the collapse of a stellar object, or they accrete matter, and because the matter they accrete can be dark matter just as well as normal matter, they should contain both. So dark matter is present in black holes. It doesn't probably dominate their behavior. Dark energy is a different matter, and it's less likely to be connected to black holes, although again, there are interesting theoretical ideas that try to connect them as well. And the reason is because dark energy appears to be a property of space-time itself and really causes the large-scale accelerating expansion of space-time. A black hole is a very localized part of space-time, and so it's really hard to see how dark energy plays much of a role in the nature of black holes.
The next question is from Hernan, who has been reading about some research. There was a system found recently that consists of a red dwarf star that's exceptionally tiny for a red dwarf star, being orbited by a Jupiter-sized planet. Can you talk about why this is unusual and how something like this system, where you have two relatively close-sized objects, form?
Right. So there are natural limits to the ratio of a planet to the star that it orbits. We see the solar system as maybe not a typical example anymore, but we see the mass range of Jupiter, by far the most massive planet, to the sun. It's a pretty large factor. And the mass ratio of this new system, recently discovered system, is a lot larger. The planet is a Jupiter mass planet, but it's orbiting a red dwarf, which is hundreds of times less massive than the sun. So it is a planet that's more massive than the star, but not by a large factor. And the question is, how is this possible? Well, two things. First of all, the planet has migrated. It's almost certain that it didn't form where it is, because in the formation of a low mass star, there's simply not enough material to form a Jupiter-massed object at that distance. So that's one thing. As for forming it further out and then having it migrate in, there's more material in the outer sectors, in accretion zones. There's enough material in principle to form the planet. And the question is, can you form the planet before dissipation, before the star becomes active and essentially dissipates the gas? And there's two theories of how planets form. There's core accretion, where you start with a rocky core. For a giant planet, it'll be maybe 5 to 10 times Earth mass. And then it attracts gas, a mantle of gas, and mostly becomes hydrogen and helium. And then there's gravitational collapse, which is just an instability in a gas disk, which very rapidly forms a massive planet. So if you push either of those theories to the limit, they can each explain in principle this new system. It's near the limit of what they can do, but these theories are not, bulletproof or completely verified. And so, of course, in any distribution of star and planet masses, you are eventually going to find objects that are sitting near the limit of what a theory can explain, but they don't break the theories of how planets form, assuming the planet didn't form where we see it now. It must have migrated in.
Paul from the UK asks, what do you think is the best hope for actual physical exploration of exoplanets? Would it be spacecraft of much faster speeds, cryo techniques for humans, small robotic fleets, or do you think that the sheer distances involved will always put this outside realistic possibility?
Well, I think if you go the route of robotic miniaturized technology, then we do have some prospects in the next decades. Breakthrough Starshot is an attempt to send nanobots, essentially very small, 1 gram mass spacecraft attached to solar cells, accelerating them with giant beamed lasers in Earth orbit to 5% of the speed of light and going to Proxima Centauri, the nearest star system. And at 5% of the speed of light, that'll get you there in a 1.5 human generations. So it's not a ridiculous amount of time. So that's a actual project that's funded by Yuri Milner, Russian industrialist, at the level of $100 million to go to Proxima Centauri with nanobots. And so miniaturization of these robotic probes is going to get us to the nearest few exoplanets on a generational timescale, if you like. Getting people and large payloads and big spacecraft to even the nearest star system is just not on the cards. The energy requirements to reach even a few percent, a couple of percent of the speed of light are just prodigious, more than the entire energy usage of the United States for a year, for example, just to get a 1-ton payload to a very small fraction of light speed, 5%, say. So that's very unlikely to happen. We need cryogenic technology, and once you have the ability to cryogenically freeze or put on ice humans, then they can make a more slow journey. They would have to be in pretty massive spacecraft to protect from radiation damage over that long journey. So there's a problem there, and that buys you more energy requirement anyway. And so for all these reasons, the fact that we don't have suspended animation technology yet, the fact that we probably need new propulsion technologies, such as fusion to power the rocket, and even then the enormous mass and energy requirement mean that I think that kind of trip is a century away or more.
The next question is from B. Mitchell 825. Have any black holes been discovered in extragalactic space?
Yes, I mean, in extragalactic astronomy, many black holes, because we think that every galaxy in the universe has a massive black hole at its core. We haven't detected black holes in all of them, but when we've looked hard with Hubble Space Telescope and very precise ground-based telescopes, we've seen the evidence of dark objects in almost every nearby galaxy, and by extension, all of them. As for whether there are actually black holes in intergalactic space, that is, black holes outside of galaxies, that also is a possibility. The gravitational slingshot mechanism in high velocity regions of a galaxy, which typically are near the nucleus, can eject one member of a companion of a binary or triple system at very high velocities, even to a few percent of the speed of light. And so you could potentially eject a stellar mass black hole that would actually leave the galaxy. There's even a slingshot mechanism which might occur in galaxy mergers, where one of the black holes at the center of one of the two galaxies that are merging actually gets tossed from the system. And so there are mechanisms by which you could either have small stellar mass black holes or supermassive black holes floating through intergalactic space.
Excellent, thank you. The next question is from Ravi, who would like to know, a writer for Quantum magazine claims that since 2011, the mechanism behind type 1a supernovas has been overthrown. Can you talk about whether you're aware of this D6 competing model of 1a supernovas, and what consequence there would be if the mechanism behind these type 1a supernova is different?
Right. It doesn't happen often, but I'm going to have to pass on this one. So I haven't read that Quantum article, Quantum magazine. It's a good magazine, by the way. And I haven't read the research paper it's based on, so I'll have to look at that.
Certainly. Renray 177 would like to know, I've heard that there are 1 trillion galaxies or 2 trillion galaxies. Which one is right?
So analogous to the difficulty of counting stars in the Milky Way, where the answer seems to be hundreds of billions, so what number is it? Counting galaxies in the universe is a difficult thing because most galaxies are faint dwarf galaxies, and it's hard to count the dwarfs. So you end up having to make a projection or an assumption of what the mass distribution of all galaxies is down to the smallest dwarfs. And unlike stars, where there is a limit, caused by the fusion limit at 8% of the mass of the sun. For galaxies, there probably isn't a limit. Galaxies can extend down to very small masses, the very puniest dwarfs, and that even starts to overlap the mass of a globular cluster, which is a component of a galaxy. So the 1 or 2 trillion ambiguity really depends on how many dwarf galaxies there are, because numerically, most of the galaxies in that count, whether it's 1 trillion or 2 trillion, will be dwarf galaxies. And by that, I mean galaxies that are even smaller and less massive than the Large and Small Magellanic Clouds, our 2 neighboring dwarf galaxies. So it's very difficult to get this census, especially when most of these galaxies to get the census are very far away, they're very dim, and they're redshifted. So it's just very challenging to count galaxies to the faint dwarf limit at any significant distance.
The next question is from Niranjan Bai, who's on with us live. Does gravity, or could gravity, play a different role at the scale of solar system as compared to the scale of a galaxy? So why don't galaxies look similar to solar systems with a central black hole and then a couple of big chunks, big things moving around it?
Well, the question about gravity on different scales is an important one, because Newtonian gravity is only tested on solar system scales. So when we go to galaxy scales and assume Newtonian gravity, we're making an assumption. And in fact, if you alter the force law of Newtonian gravity from inverse square to a number that's not quite a power law of -2, you can actually do away with the need for dark matter. So that's how sensitive these calculations are to the gravity law on large scales, because it's essentially an infinite force law. So the fact that we can't really independently test Newtonian gravity on galaxy scales is a bit of a limitation. We end up having to make that assumption that it's valid. And that sort of is it's a big asterisk around all the discussions of gravity on large scales.
The next question is from Ron CC1. If the universe is expanding, is it correct to say that space-time itself is expanding? And if so, can you tell us if there are any consequences for the time dimension, like if that is expanding and slowing as well?
Yes, it is correct to say that space-time itself is expanding. The expanding universe in the model, in the theory of general relativity, is a space-time manifold. Manifold is a mathematical term for a sort of geometric structure. In this case, it's a physical structure, space-time, 3 dimensions of space and 1 of time, that are hyphenated because they're together, they're linked in the theory. And in general relativity, the expanding universe is the expansion of the grid of space-time itself. And that's essentially how we must understand it. There's a second part of the question that I missed.
Sure. The question is, are there any consequences for this expansion on the time dimension?
Right. So expansion of the universe is space-time expansion, and the question of whether the expanding universe affects time is a good one, because it does actually. So in general relativity, there's ways of defining time. However, time in general relativity depends on local gravity. So the way you define time depends on the gravitational situation. So in the depths of intergalactic space, where there are essentially no objects, just a thin smattering of dark matter, then that's the gravitational context for time. But where a massive object exists, then time will be going slower and it will keep its own clock. So yes, because the expanding universe is filled with physical astronomical objects, and because time varies according to local gravity, you have to work out the gravitational situation at every place to understand how time varies at that place.
The next question is from Yangip, who would like to know, in the James Webb pillar of creation data, black dots appear in bright centers different from the Spitzer images. Do you have any ideas about why these phenomena seem so much like black holes? Could we be seeing black holes forming in these star-forming regions?
I don't think we're seeing black holes in these type of images. Remember that when you're looking at either Spitzer or James Webb, you're looking at infrared. You're looking at quite significant mid-infrared wavelengths. That's the thermal infrared. and that is actually as a way of looking deep through dust. And so you can see to where stars actually form. Very few of the stars that are forming in these regions are going to be black holes, so I don't think black holes are involved. However, there are dusty enough regions that even in the infrared, even with long wavelengths, the light doesn't get out. So you can have opaque regions. They're just different from the opaque regions you see in a visible image, because in a visible image, it takes far less dust to make a region opaque and dark than it does at infrared wavelengths. So that's the main difference. But there shouldn't be a dramatic difference between what Spitzer and James Webb see, with the important exception that James Webb has better angular resolution. So it's going to see sharper features on any scale.
The next question is from Thubin JP. Obviously, this is just spitballing, but do you have, but you have some experience bringing information to the public. So in what ways can we take this knowledge of astronomy out and back to society, especially young children in a country like India, where their exposure to such knowledge is still very rudimentary?
It's a good question, and I think, anyone, professional astronomers, certainly have an obligation to communicate to the public and broadly to not just their tribe of astronomers. And it's a big need to have more science out there in the community. So if you live in a place like India, or I've been 8 or 9 times actually, and I've given talks in schools and in community centers and small locations in the south and north of India. I think you just have to get out in the community. You have to just find your local, if the place you live, if it's a big city, then maybe there are local places. There are certainly always schools and probably teachers who would be very happy to have someone tell their kids about astronomy, because they may not know anything about it. So just reach out to the local schools. Maybe there are libraries that have talks. There are various public events where science is presented, and you can just volunteer yourself as a lecturer or a speaker on a particular astronomy topic. So there are a number of ways to get involved locally. And I bet for astronomy, which most people like, even if they don't know much about it, I think you'll find receptive audiences.
And this is also common in the United States for amateur astronomers, is, to get out. There are lots of resources from, for example, the the Astronomical Society of the Pacific has a whole network of amateur astronomers. I can't think of the name of it right now, but they have a whole system and resources. So there may be things that you can take, talks available.
Yeah, I think it's called the Night Sky Network.
Thank you. Yes, that's correct. I appreciate it. The next question is from Wendy Traver. Is any research currently being conducted in cryobiology, so that in the next centuries, trips to the local group may be possible? Basically, are we any closer to freezing people so that they can travel beyond our solar system?
Yes, there is. The research, of course, is fairly controversial, because it's applied to humans. There are enormous ethical issues, and there are even ethical issues when it's applied to animals or mammals, because if you want to see if something will work on people, you have to use the best animal models, which are mammals typically. Obviously there are places like Alcor, which is up in Phoenix, where cryonics has been going for decades actually. So I think they first started putting people on ice. It's not ice, it's liquid nitrogen they're frozen to, maybe half a century ago, and people are still going there. But that's not a scientific experiment, because we simply don't know what will happen, and in all likelihood these people can never be reanimated. Medical researchers, however, have made some significant progress. So it's not really coming from astronomy, but from medical science. And it's coming because, of course, there are many cases where people fall under ice in a frozen lake and have to be reanimated, or there are enough examples of people who've been suddenly shocked into a very cold state where their metabolism slows down dramatically. And so keying off that, people have started to develop ways to do that deliberately and take people down to a low metabolic state. The more dramatic version of that, which is probably required for true interstellar travel, is to replace all the body fluids. You can't freeze, you can't take someone down to a very low metabolic state without actually freezing them. And as soon as you freeze them, because water expands when it freezes, cells burst. And so, the biology is disrupted, and and the organism essentially dies. So what you actually have to do is replace the blood with a compound that's partly glycol and partly other ingredients, and a very stable fluid, which is still a good medium for the synthetic blood chemistry, if you like. And these experiments are being done on pigs and dogs, as far as I know, not on humans. There's no agreement of how we would give permission to try them on humans, with some moderate success. Pigs and dogs have been taken into 1% of normal state metabolically and reanimated after days, weeks, in some cases, not with full success, but some significant success. So I think you play that research forward a few decades and it might actually reach the level where it will work on people.
Thank you. The next question is from Prad 1307. What is the basic difference between the quasi-steady state model and the Big Bang model? Why so far is the Big Bang model superior?
Well, the quasi-steady state was just an adjustment of the steady state model to, allow changes, to allow evolution in how the universe appears. In a pure steady state model, you can have expansion because things move away from each other and there is space being created at a continuous slow rate in the vacuum between galaxies. So you have evolution, but overall the universe looks more or less the same at any point in the past and the future. Well, we know that's not the case because the universe was hotter and denser in the past. And even if there wasn't a Big Bang, that data is pretty convincing. So quasi-steady state is just a way of incorporating an evolving universe, which was hotter and denser in the past, but without having the actual Big Bang itself.
The next question is from one of our live participants. I've been seeing online videos showing the solar system going around the Milky Way at a perpendicular angle. I always thought that our plane was similar to the galactic plane. Which one of these is correct?
I think anything that shows perpendicular is not correct. It's pretty easy. You can see what the plane is because you just have to go out on find a good dark sky, and you can see the plane of the Milky Way. And if there's any planets visible, you can connect the dots between the planets and the sun and the moon and see where the ecliptic is, and that's the orbital plane of the solar system. And they're a few tens of degrees different. They're not perpendicular to each other.
The next question is from Jorge. If we plan to go outside of the solar system, I get the general question is, don't you think our spaceships should be shaped, or does the shape of the spaceship that travels beyond our solar system matter? They speculate, this question asker speculates that they should be more round and thin, sort of like the shape of a solar system. But can you talk about the shapes necessary for space travel?
I think once you're in the vacuum of space, the shape essentially doesn't really matter at all for travel because you have no drag, you have no medium that you're traveling through. It's incredibly sparse. And so there's no resistance, there's no drag in that sense. So for that reason, the shape doesn't matter. The reason the shape matters, of course, is for the ergonomics of space travel. So you want the strongest and most efficient structure, and because it's going to have forces and stresses inside it, it's going to be pressurized, it's going to support people inside, for example. Maybe you want to have artificial gravity, in which case you'll make a toroidal structure and spin it up, as in the movie 2001. So there are all sorts of configurations you can have, and the geometry is not really constrained by the fact that you're in space, because you can pretty much make whatever you want. It's constrained by strength to weight ratio and whether you want artificial gravity or not, and the nature of keeping your entities that are in the space station surviving and alive. You also should worry about radiation cladding, and in that sense, the most efficient shape for any traveling object is a sphere, because it gives you the maximum surface area per volume, and that helps you protect whatever's inside the spaceship.
The next question is from one of our live participants. Pasta Pastor asks, I have looked started to look at the Fermi Paradox, which last week, I think or last session we talked about. People are no longer referring it to as a paradox. You can refresh our memory about that. The universe is old while we are young, but does this Fermi conundrum take into account that the early universe was likely not very habitable?
No, the Fermi paradox, and it is really just the Fermi question, the where are they, given that we should expect other intelligent entities to be around. It's mostly posited in the present day galaxy. It is, however, the case that there have been billions of years for evolution of intelligent technological civilizations, including many billions of years before the Earth formed. So the time dimension is absolutely important, but you don't have to take it all the way back to the Big Bang. A billion years after the Big Bang, there were mature galaxies, a lot of carbon had been made, there was water, there were planets, stable planets. And so you could certainly have intelligent life. And if it got a start then, that's still 7 billion years before the Earth formed. So you still have plenty of time to evolve complex creatures before we even get a start on our planet.
The next question is from Lawrence 4040. Are there other ways in which black holes lose mass or energy other than Hawking radiation?
Not that we know of. Black holes are essentially tombs of matter. Their self-gravity is so strong that they maintain the mass within the event horizon where nothing can escape. And so Hawking radiation is the only physical mechanism we know of whereby the mass of a black hole decreases rather than increases.
The next question is from Wendy Traver, who would like to know, do you think that if human vision fell into a different part of the electromagnetic system, that life would be possible?
It's clearly possible to have life that doesn't require a visible light, because we have creatures in the oceans of the Earth which sense magnetic fields. Some of them, they don't have eyes at all. They just have magnetic sensing organs in their skin. And we of course have a variety of creatures that use infrared vision. That's some in the oceans, and snakes do, and so on. Also, we have ultraviolet sensing creatures on Earth. So there are adaptations of creatures that live in darkness or at night on the surface where non-visual radiation has always been required. So it's completely reasonable to expect biology elsewhere in the universe to have evolved these strategies as well. Our eyes are tuned in their sensitivity to the radiation spectrum of the sun, which has an equivalent temperature of 5,700 degrees Kelvin at the surface. If life evolved on around a red dwarf star, there'd be very little visible radiation and a lot more far red and infrared radiation. So then again, you'd have infrared sensing life. So I think life will readily adapt to the wavelength where the information to be processed is coming out.
The next question is from Jestal88. Are we any closer to understanding the dark ages of the universe since the launch of the James Webb Space Telescope?
We're a little closer. James Webb is still in its first year, so it's reasonable to give it some time. It hopefully will run for 10, maybe 15 years. And it's already done some deep surveys that have looked and found very mature and maybe even surprisingly large galaxies within about 300 to 400 million years after the Big Bang. And then a 14 billion year old universe, that's pretty early. However, it's not finished its work, and following up these objects with other telescopes and measuring redshifts is quite hard. It needs ground-based big telescopes or many observations with James Webb in spectroscopy in different ways. So we think we will probably be able to push back to maybe 100 million years after the Big Bang. And in most theories of evolution of the hot universe, that's the earliest you can imagine forming galaxies. But we may be surprised by the data.
The next question, it's actually a follow-up to that one. Have there been any other major discoveries since the telescope launched? Can you talk about something that you have found interesting or that has been surprising that you think is a major impact?
Well, the recent discovery of very large and mature seeming galaxies within 500 million years of the Big Bang. That is a bit of a surprise because the standard models of galaxy formation are hierarchical in nature. That means they're called bottom-up theories, where the smallest objects and galaxies form first, dwarf galaxies, and they gradually merge and combine to form larger galaxies. So it takes a while to build a big galaxy. And yet big galaxies, as big or bigger than the Milky Way, have been seen in these very early epochs. And it's a challenge to the theories of galaxy formation. It doesn't rule them out or say that either the theory or the data must be wrong, but it's definitely a challenge. So we think now, because of this, the galaxy formation is happening earlier than we thought in the young hot universe, and black hole formation of the center of those galaxies is also probably happening earlier and faster than we thought, because we see mature billion solar mass black holes within 500 million years of the Big Bang.
The next question is from an email. When looking for life in the cosmos, wouldn't it be important to consider single star systems such as our sun before multi-star systems, perhaps due to long-term stability?
Sure. It's a lot more likely that you'll have a stable set of planet orbits around a single star, but a lot of binary stars are actually wide binaries. So there are binaries that are very tight, where they almost exchange mass between their envelopes, and contact binaries, as they're called. And in those systems, planets with habitable orbits probably couldn't survive. They would be consumed by the stars or ejected. But there are many wide binary systems where, when the gap between the stars is thousands of astronomical units, you can have an entire solar system like ours orbiting the star without perturbation or without mayhem for billions of years. And so, yes, there easily can be a lot of planetary systems in binaries or multiple star systems, as long as they're loose systems and not tightly bound systems.
The next question is from Sour 2098. A comet disconnection event is when the head of the comet somehow disconnects from the tail. Are you familiar with this phenomena? And can you talk a little bit about if this has ever been observed, or if you're familiar with how these kinds of events occur?
I don't think it's been observed in the recent past in a way that we can easily document. I do understand that it's theoretically possible to have such a disconnection event. The tail of a comet is just that sort of glowing plasma, which is from the ablation of material, because remember, you have rocks and ice mixed in a comet, so there's chemicals being ionized and blasted off the comet and blown away by radiation pressure to form a tail. That tail could, in principle, get detached, and we've certainly seen comet tails that sort of break up and bifurcate and almost fragment. The full disruption is pretty rare, but I understand there are theories that say it could happen. I can't think of an observed example in the last decade or so, though.
The next question is from an email. Does the second law of thermodynamics encapsulate the arrow of time, or is the arrow of time only a mental construct?
Well, the arrow of time is a mental construct, because our conscious experience of the universe is that time flows in one direction. It's an irrevocable part of the human experience. So it's a mental construct, but yes, it goes beyond the mental construct to the realm of physics. And the second law of thermodynamics, the sort of tendency towards chaos and disorder that's encoded in that second law, does appear to be related to the situation of time moving in one direction and not in two directions. Boltzmann defined entropy as the number of equivalent microscopic states. So when you go from a more specific arrangement of atoms or particles to a more generic distribution of particles, then you end up increasing entropy, and that's the tendency towards disorder that we see all around us. So it does seem that the second law of thermodynamics is implicated in the arrow of time, because we simply do not observe situations where entropy spontaneously decreases.
The next question is from Waniac 6260. Has there been a sudden shift in the Earth's rotational axis recently. Can you talk about how these shifts have occurred in the past?
No, we have geomagnetic data now that's pretty reliable going back millions of years. So we see no evidence for the Earth's axis of tilt changing, but we know that the geomagnetic axis does shift. It shifts by a few degrees. So there is longer term indirect evidence for this shift. Just there's no evidence that it's happened in recorded history, for example.
The next question is from Goldilocks Zone. Could an intelligent life, I mean, really, I think we could go all the way to, could life at all form inside or exist inside a star? Obviously, it would be nothing like us, but could something else be there?
It's very unlikely. So it's simply because of temperature. So all stars, whether they're red dwarfs or stars like the sun or more hot or massive stars, all stars are plasmas. So the fundamental state of matter, even at the edge of a star and certainly deep in its core, is a plasma. And that means the electrons have been stripped off the protons, if it's hydrogen, or electrons stripped off the heavier nuclei, if they're heavy elements. And in that sense, you can't make chemical structures. So there's no such thing as a chemical bond in a situation like the interior of a star. And if you can't have a chemical bond, then you really can't have biochemistry. And if you can't have biochemistry, you can't have life. So I think the odds are no life inside stars, even if it's stranger than we imagine.
All right, the time is now 10:53. We want to make sure that you get to your meeting on time. We're going to do one last question, and then we're going to end for today. David McKenzie would like to know, at what point in the history of the universe could life as we know it have taken hold? So I guess the question is, how early in the universe is it possible for life as we conceive it to have formed?
It's a good question, and we don't know the answer, but I can speculate as to what the answer will be or might be. All you need to have life, assuming it has base requirements of carbon-rich material, water, and a suitable energy source, all you really need is enough chemical history of the universe for the first few generations of stars to have been born and died. And since star birth and death of massive stars, which form the heavy elements anyway, is very rapid, it really only takes a few million, maybe tens of millions of years to put enough carbon in the universe that in principle, and heavy elements, that in principle you could have planets and therefore biology on those planets. So the theoretical limit to that is very early. Now, the universe may not have been conducive in a general sense to biology for some time later, but the earliest potential time, hypothetically, for life in the universe is really early. It could be as little as 30 or 50 million years after the Big Bang, which is incredibly early. That was a very hot, dense universe compared to the one we live in now, which wouldn't in and of itself preclude life. Thanks. It was a good question to end with, and a lot of good variety as usual. Appreciate your questions as always, and thanks to Matthew and Vicky for facilitating. And I think we have one scheduled. I'm on a trip to Denmark for our spring break, and we'll be back the following week. And I think we have a session scheduled for that week, but I don't remember when.
That's correct. It's 2 weeks from now. I don't remember the exact date, but I will send it out. It's March 15th. So okay. We will see you all in 2 weeks, and that will be on YouTube. We hope you have a good rest of your week and a wonderful weekend. Take care, everyone.
Okay, bye.